Whiteboard Physics A-Level Lesson 73. Moving on from GCSE. Now this lesson is focused on practical work in physics, which was one of the big 3 strands of skills that you need to know for your A-Level Physics. So let's just start with that, the 3 strands of knowledge that you need to have. In order to succeed in A-Level Physics, you need, let's write this as the 3 knowledges. That's what I tend to call these. Knowledges. You need to have mathematical skills. Now, I cannot help you develop them. You need to develop your own mathematical skills by doing questions from Isaac Science, Isaac Physics, or any of the drill questions that are available on my website to enrolled subscribers, all that sort of thing. The second of the 3 knowledges are your linguistic skills. Now, I can show you the sorts of technical words that you need to be using, but then it becomes your responsibility to use them. So all the way through my lessons, I use technical language, I write down technical words, but you've got to absorb that into your everyday lexicon. And the third are practical skills. And that's what we're going to focus on over the next few lessons. So those are the 3 knowledges, actually for GCSE physics as well, but they become very important for A-Level Physics. So when we talk about practical skills, we're talking about moving on from GCSE level. Now at GCSE level, it is quite common that for practicals, you'll turn up having done no preparation in advance. You'll be told exactly what to do. You'll do it. You might even be given a table to fill in or told exactly how to design your table. Then you'll be told what safety things you need to look out for. You'll be closely monitored throughout. And then at the end of it, you might be given guidance on how to process the results, what the graph should look like, and then finally, how you're going to write your conclusions. Now in A-Level, we step up. You take over all of those tasks. Not all at once, usually, but you will, by the end of the A-Level, be doing full investigations from start to finish all by yourself. And one of the most important things when it comes to practical skills is safety. Now, it is not required for you in A-Level to do full risk assessments for every practical that you do, but you should be assessing risk. So what do I mean by that? I mean a short statement, a sentence or 2, just to identify any hazards that are present in a practical investigation that you can foresee, and maybe a statement or 2 about what you can do to reduce the risk from those hazards. So you don't have to do a full risk assessment where you write down a numerical value of the risk and the numerical value of the impact of that risk and so on and so on. But there should be consideration of hazards and how to reduce risk. Now, when we talk about risk, we are talking about the risk of harm to a person. We're not interested in breaking the apparatus. Obviously, try not to. Risk of harm to a person is what we're interested in. Usually, it would be you doing the experiment, but not always. There's a required practical where you use lasers, and there is a risk to other people in the room, for example. So safety is a big concern. Now, obviously, your teacher will still have overarching responsibility for safety. You can't accidentally chop your leg off and then the teacher say, well, they didn't do a proper risk assessment, so it's their fault. It doesn't work that way. But the responsibility should be being shifted over. Now, in the workplace, responsibility for safety is everybody's responsibility, the employer and the employee. And that's what we're really preparing you for, is real work in the laboratory, where it's not just whoever runs the laboratory that's responsible for your safety, but you are also responsible for your safety. And so we're preparing you for that. At university, for example, yes, the university is still liable for accidents in the laboratory, but so are you. So you do have to take care. The second issue is group work. Now, different schools run things in different ways. Some schools will let you decide who you are working in a group with. Some will allocate you groups, and some will switch between them. In A-level, there are, and we'll come to this later on, there are practical assessments. AQA calls them required practicals, Edexcel calls them core practicals. But there are these required practicals, these core practicals that every student has to do. And they're assessed, which means that your teacher has to assess your competency in different areas, including following instructions, thinking scientifically, making justifications of choices you make during the experiment. But we'll get to all that later on. So the issue in group work is that the groups should be as small as possible. Ideally, a group of one, just you by yourself, but that's not practicable in most schools. And the reason why we want the groups as small as possible is because everybody must participate in all aspects. So it's quite common for a teacher to walk around and ask questions. There might be questions about safety. We've already mentioned safety. And they might take each of the students separately, walk away from the experiment with them, and just talk to them individually and say, okay, tell me about the hazards you've identified. And what you can't say is, oh, I didn't do that bit, my partner did it, because then that's a fail on competency 3. So everybody has to participate. If there's measurements being done, everybody has to take a part in doing those measurements. If there is any sort of analysis to be done, everyone has to analyze the data. When it comes to recording results, which we'll get onto in a second, everybody has to record the results in real time at the same time. So you need to work with others in a group, yes, but it's not the case of you're in a group with one person doing all the work and you can just sit back with your feet up. It doesn't work that way, because if you do that, you're not marked as a group, you're not assessed as a group, and you will end up underperforming, potentially even being at risk of not getting a practical endorsement. And again, we'll come to all that later. The next thing is planning. You do have to be responsible for doing some planning of practical activities. Now, what does that look like? Well, it could be that you are given a very basic title, investigate stationary waves on a string, for example. It's very open-ended practical, and you think, well, what am I investigating? So when it comes to planning, you've got to think about what your variables are. So what is your independent variable in this particular practical? What is your dependent variable? What are your control variables going to be? How are you going to make sure you keep the control variables the same? So just a reminder, the independent variable is the one that you impose your will on. Imposition of will. Sometimes it's called the one that you change, but I don't like that as a phrase, because there could be plenty of situations where you are making a change to the dependent variable to see what value it has to be, given an independent variable that you've chosen. So this is the one on which there is the imposition, I'm just improving my handwriting here, of your will. So I am choosing these values. Then there's the dependent variable. And this is the one that the universe decides for you. So this changes, and if it doesn't change, it's not a very good choice of dependent variable, changes as a consequence of the independent variable. So you've made some change, and then the universe responds by changing some other variable as well. That's the best way I can use to describe it. Both of these variables will show change, but the independent variable is the one with the direct imposition of your will, and the dependent variable is the one where you don't get to choose what it is, the universe does, and then you just measure what happens. But you're measuring both the independent variable and the dependent variable. So sometimes you'll see the independent variable is the one you change, the dependent variable is the one you measure. Well, it's not good enough because you also measure the independent variable and you measure the control variable. Control variable. I've heard all sorts of variable songs on YouTube and other mnemonics to help people remember these, and they might be okay for GCSE level, but usually students don't understand what these variables are, and those little songs and mnemonics really haven't helped. So the control variable isn't just one that stays the same, it's one that you choose to keep the same. So this is imposition of will to keep the same. Imposition, you impose your will to keep the same. So you can't, let's change that to change. You can't just say, oh, well, the control variable is one that stays the same. What about speed of light? Speed of light stays the same. But we would never list the control variable being the speed of light because we haven't done anything to try to keep it the same. It just is the same, like the charge of the electron. We do an experiment with electron charges. We can't then say, well, the charge on the electron is the control variable. No, because we haven't done anything to try to keep that the same. That's just the way it is. That's just a constant. So what are control variables? Well, it could be something like the temperature of the room in which you are, or the pressure of the room in which you are, if you're doing some sort of thermal physics experiments. And you might think, well, I'm not doing anything to keep that the same. Well, maybe not. But if you're performing the experiment on the same day, over a short period of time, why would you choose to do that? Why not just drag it out over multiple days, across a week, across a month, across a year? Why would you try to do it all on the same day? Well, because you're going to want the same atmospheric pressure, the same temperature. So, things like that are control variables because you are doing things to keep them the same. And when it comes to these variables, you don't just say, all right, I found out what these variables are. You then have to state or decide how to change them, control them, keep them the same. I don't know what we'd word that as, how to manage them, how to, I don't want to use the word control because the word control is found in control variables. So let's say state how to manage variables. How are you going to make that change, impose your will? How are you going to do that? How are you going to make those measurements for your dependent variable, for your independent variable? How are you going to make sure that the signal generator shows the same frequency? Now, things like signal generators, as they run, they heat up, and that can change the internal resistance, which can change the circuit. I don't know how, I'm not an electronics engineer, but it can change the frequency slightly that's being given out by a signal generator, even if you don't change the dial. So good advice is always to leave signal generators on for a long time, for a good 10, 15 minutes, even 20 minutes, maybe even half an hour if you can, before using them, so that they settle and you get a particular frequency for a particular setting on the dial. There's no guarantee, of course, and the frequency it says on the dial is the frequency you get, so you're going to have some way of measuring that frequency, even if you're keeping it the same, because very often, actually, part of the investigation would be to determine what the control variable values are based on the experiment you've done. So you've still got to be able to measure them to check that the experiment was successful. And all of that needs to be planned. Now, when you plan those things, you can go ahead and look up investigations. You can do research into planning, and that's absolutely fine. But if you're going to do that, then you have to actually reference where you're doing that research. So we've decided what we're going to investigate. We've got our variables and everything else. Then we have to decide the methodology. Methodology. The experimental procedure. We have to decide the instruments we're going to use to make measurements. That's what we call things that we measure with, instruments. You know, what if it's an electrical experiment, what meters are we going to use? With what range? With what sensitivity? And why? Why would we choose to use those meters? You might have to do a preliminary investigation just to find out what a range of values you expect would be, and that will help you decide which scales on your meters are most appropriate. That's fine, but you've got to record all that stuff that you're doing. Don't just look on the shelf and say, oh, there's a meter, I'll use that one. That's not advanced level physics. That's what you did at GCSE level, just using what you're given. And then you might have to think, what am I trying to find out? So decide the outcome. That says thou. The outcome. Because that's what you're going to be judging yourself against, the outcome. What were you expecting to get? And how do you know, you got a value, was it what you expected? And how do you know that it's not what you expected? So how do you measure success? I think there's 2 C's in success. Or maybe there's only 1 C in success. Oh, I don't actually know. I'm going to go with 1 C, and if it's wrong, go in the comments and let me know. Boosts my engagement on these videos. So how do you measure success? I feel like there's 2 C's. Right, so you've decided what your variables are. You've decided how you're going to manage those variables, your methodology for doing your experiment, the instruments you're going to be using, what you expect the outcome to be. How do you know that's what you expect the outcome to be? You've done all your planning. And now you do the investigation. And we're going to talk more about the doing of the investigation next lesson and the next few lessons. But an important part is how you record results. Now, when you record your results, there is a way of presenting tables. You always got to use tables. Don't just write down lists of numbers. I see this all the time where students just write down lists of numbers, and they'll say, oh, I'll add the lines onto the table later. Well, that's fine, but if you haven't written headers for the lists of numbers, table headers, column headers, then how are you going to know what these lists of numbers mean later? Or their list of numbers will be in some very odd arrangement that's non-standard. So we can just write down a few numbers. If, for example, we're measuring a wire length, then that's a single measurement. So single measurements, like wire length, don't need to be in tables. They just need to be written down, but you can do repeats. So single measurements, such as, let's go a wire diameter. You wouldn't measure it for every single time. Let's say you're doing resistivity of a wire. You're measuring the resistivity of a wire. So you're changing the length of the wire and measuring the resistance of the wire of that length. But you're going to keep the diameter of the wire the same each time. That's a control variable. But you still need to measure it. So such as a wire diameter, what you would write down is, let's use a different color for this. You would write down something like diameter of wire. Pen stopped working. Diameter of wire. So you've written what it is. Then you might give it a symbol that you can use in your analysis later. So do remember to give yourself a symbol. Then you don't have to define it later. It's also quite helpful, especially if you're taking repeats, to include the unit at this stage. So why are we including the unit there? Well, I'll come to that in just a second. Let's say that the wire diameter was 1.00 millimeters. Well, what I've written there is D divided by millimeters is 1.00, which is exactly the same as D equals 1.00 millimeters. You see, we just rearranged it. We just multiplied by millimeters to get this statement here. The variable D contains the unit millimeters. So by dividing by millimeters, that unit disappears, and I'm left with 1.00. So it can be helpful to do that. Now, if you're taking repeats, you might do something like this. And maybe you'll do a few repeats. Now, really, we want to do 7 repeats for interesting reasons. But if the numbers are close together, then that might be a waste of time. So at least 2 repeats. So that's 3 values measured. So let's say at least 3 times. Ideally 7. Okay, so that's single measurements, and you'll have them on your page clearly laid out. You know, diameter of wire is very clear under a subtitle that says what the data is for. All tables, all data, make it clear. So you might have an experiment that has multiple parts to it, and you need to know what those different parts what value those different parts would have, or something. There's lots of different parts. There's different tables for each part. There's different values for different tables and different parts. So what am I going to do? Well, I'm going to do subtitles and captions on my tables as much as I can, so that when I come back in a year's time, I understand what I've written. So let's say I'm doing this experiment where I'm measuring resistivity. So I'm now going to draw a table. And when I draw my table, there's a certain layout. So draw table. The column order should be independent variable to the left, independent. That should be to the left. Then any dependent variables, dependent. Then any processing that comes after it. Now, you might put processing between independent and dependent as well. That's okay. You might need to do that as well. And you might have to do repeats as well. So there'll be multiple sub-columns, if you like. But that should be the order. The independent variable, the direct measurement of your independent variable should be the column on the left. And then the dependent variable should be after that. Any control variables, because they should be staying the same all the way through, they should be listed separately, not as part of the table. So your results might look something like this. Let's just put example. Your results table for the experiment where you're measuring resistivity might look something like this. We're going to have wire length, and that's going to be L in, let's say, meters. There we go. And I'm only going to measure that once. And then I might be using a resistance meter. So I will have resistance. How do I spell resistance? Resistance in, maybe it'll be in ohms, might be in milliohms. And I might get first set of results, second set of results, third set of results. And I could go up to 7, but maybe I won't bother. Just like that. And actually, that's it. I'm done. I don't have to do any processing. That's all the information I need. All there's one little bit of processing, which would be average at the end. So I could put average resistance or mean resistance in ohms. So there's the processing. And then you get your ruler out and you draw your lines. And I would draw the lines sooner rather than later, because I think it really helps keep things neat, and it prevents your columns from going diagonal and wandering across the page or something, which can be a little bit confusing, and then you end up with really skewed tables which just look bad. Probably doesn't matter, but it just looks bad. So column header, you don't need to draw a line between every single between every single row. That's unnecessary, especially if you're using lined paper. But what I will do is I'm going to instead draw this here. And I'm going to say this is resistance. And we've got the first set of these, the second set of these, and so on. So that's what the table might look like, something like that. And then beneath it, we might have wire diameter D in millimeters is equal to, and that's probably all the information we need with the repeats. And then you can have mean or average wire diameter D in millimeters is equal to. Well, you calculate that. Of course, I've missed something. Did you spot what I missed? I wonder if you did. I missed the symbol. It's not the end of the world if I've missed it. It just means that I've got to define it later, and that's a bit of a faff. But I missed the symbol. Symbol for average, we can use the triangular brackets. I'm going to cheat and make this smaller so I can actually get it all. I'm going to cheat and make that smaller. Ha 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 ha. Make it fit. Can't do that with pen and paper. That's going to be pen stopped working. That's going to, why is my pen stopped working? Why is my touchscreen stopped working? There it is. That's going to be average R. You can use the triangular brackets for average. That's fine. Let's just get rid of that blob there. Right, there we go. And that would be a nice way of laying out a table. So independent variable, the thing you're choosing to change, that's on the left. Oops, that's on the left. Then to the right of that, we've got our dependent variable. So there's our independent variable. That's what we're directly influencing. We then measure the effect on a bunch of resistances, and then there's any processing, calculating the average. What I also find helpful is before plotting a graph is redrawing the table just for what's going to be on the graph. You don't have to, but I think it's quite helpful to say, okay, this is what's going on the x-axis, this is what's going on the y-axis. And sometimes you'll have to do some processing for that as well. But there'll be more information about how to do processing of data later. I think we should stop there for this lesson. So that is a good introduction to some of the extra complexity moving on from GCSE. The next lesson we'll talk about making careful measurements. I hope you'll join me then. Bye-bye.